Welcome to this video where we dive into the world of silica and explore its different types. Silica comes in many forms, but in this series, we'll focus on the ones most relevant to the adhesives and resins industry. We will take a quick look at the various types of silica, then zoom into fumed silica and precipitated silica, two of the most commonly used fillers in industrial applications. Most importantly, we will discuss how silica plays a key role in epoxy adhesives formulations, improving performance and enhancing critical properties. So let's get started. Before we dive deeper into our discussion on silica, let's first clear up some common terminology to ensure we're all on the same page. These terms, silicone, silicate, and silica may sound similar, but they refer to very different materials with distinct properties and applications. Starting with silicon, Si, the elemental metalloid. Let's start with silicon, a fundamental chemical element with atomic number 14, belonging to the carbon group in the periodic table. As a metalloid, it exhibits properties of both metals and nonmetals. Silicon is the second most abundant element in the Earth's crust, mainly found in the form of silica and silicates. Its properties of both metal and nonmetalloids. It is an essential material in the semiconductor industry, forming the backbone of modern electronics such as microchips and solar panels. Beyond electronics, silicon plays a crucial role in glass, ceramics, construction materials, and even as a reinforcing filler in polymers and adhesives. In its pure crystalline form, silicon has excellent thermal and electrical conductivity, making it indispensable in high technologies industries. Silicone, the versatile synthetic polymer. Next, we have silicone, spelled with an E in the end. Unlike silicone, which is a natural element, silicone is a man-made polymer composed of silicone, oxygen, carbon, and hydrogen. It exists in various forms, including liquids, gels, elastomers, and resins, which tailored for different industrial and consumer applications. Silicone is highly valued for its flexibility, water resistance, chemical stability, and heat resistance, making it an ideal material for medical implants, adhesives, lubricants, sealants, and coatings. While silicone is a rigid crystalline material, silicone is a soft, flexible polymer with a completely different set of properties and uses. 3. Silicates, the mineral giants. Now let's talk about silicates, which are a vast group of minerals composed of silicon and oxygen, often combined with elements like aluminium, magnesium, and iron. Silicates make up over 90% of Earth's crust, with well-known examples including quartz, feldspar, mica, and clay minerals. These minerals are widely used in ceramics, glass manufacturing, cement, and refractory materials due to their thermal stability and durability. Unlike pure silicon, which is used in electronics, or silicone, which is flexible synthetic polymer, silicates are naturally occurring inorganic compounds that play a key role in both geological and industrial application. Finally, 4. Silica, SiO2, the core of this discussion. Finally, we arrive at silica, also known as silicon dioxide, SiO2, the primary focus of this series. Silica is one of the most abundant minerals on Earth, found in sand, quartz, and various rock formations. It is an essential material in glassmaking, ceramic, and concrete, and serve as a key filler in rubber, adhesives, and coating due to its hardness, chemical resistance, and thermal stability. Unlike elemental silicon, which is a semiconductor, or silicone, which is a synthetic polymer, Silica is an inorganic oxide with remarkable structural strength and a wide range of industrial applications. It is also a raw material for producing silicone and silicate, further demonstrating its importance in various industries. Before diving deeper into silica and its role in epoxy formulations, it is important to understand a fundamental concept: crystallinity. The way atoms or molecules are arranged in a material significantly impacts its physical, chemical, and mechanical properties. Crystalline solids, the ordered structures. Crystalline solids have a highly ordered atomic structures, meaning the atoms, ions, or molecules are arranged in a repeating three-dimensional pattern. This regular structure results in a distinct geometric shapes, sharp melting points, and well-defined cleavage planes, which means they tend to break along specific directions. As you can see in this image, the precise periodic arrangement gives crystalline solids unique properties, such as anisotropy, meaning their characteristic like strength and conductivity vary depending on direction. Common examples of crystalline solids include metals, salts like sodium chloride, and minerals such as quartz. Their well-organized atomic structures contribute to their optical clarity, electrical conductivity, and mechanical strength, make them essential in industries such as electronic, constructions, and material science. This is why crystalline silica, which we'll discuss later, plays a crucial role in industries' applications. Then we have amorphous solids, the disordered state. In contrast, amorphous solids lack long-range order in their atomic arrangement. Their atom or molecule are distributed randomly, more like a frozen liquid rather than a neatly arranged crystal. Because of this, amorphous solids do not have a sharp melting point. Instead, they soften gradually over a range of temperatures. Examples of amorphous materials include glass, rubber, and many polymers. Unlike crystalline solids, they are typically isentropic, meaning they have uniform properties in all directions. This random molecular arrangement often leads to properties such as greater flexibility, impact resistance, and optical transparency. That's why amorphous materials are widely used in applications such as optical lenses, coatings, and adhesives, where flexibility and tunability are more important than rigid structure. While crystalline materials offer strength, stability, and precise performance, amorphous materials provide versatility, transparency, and adaptability. Understanding this distinction is essential when selecting materials for adhesives, coatings, and fillers like silica in epoxy formulations. Understanding porosity, porous versus non-porous materials. Before we dive deeper into silica's role in epoxy formulations, we need to discuss another important structural characteristics: porosity. The presence or absence of pores significantly influence a material's mechanical properties, absorption capacity, and industrial applications. Porous materials or the absorbers. Porous materials contain a network of interconnected or isolated pores, allowing them to absorb liquid, trap gases, or facilitate permeability. These pores can vary in size, shape, and distribution, affecting how the material interacts with its environment. Porous materials can be natural, like wood, pumice, and certain rocks, or synthetic, such as foam plastics, activated carbon, and aerogels. Their porous structures provide high surface area, lightweight properties, and excellent thermal or acoustic insulations. Because of these attributes, porous materials are commonly used in filtration systems, catalysts, adsorption, and biomedical application where the ability to retain and transport fluid or gases is essential. Non-porous materials or the barriers. On the other hand, non-porous materials have a dense, continuous structures with no significant voids or openings. This makes them impermeable to liquids and gases, meaning substances cannot pass through their surface or structures. Examples of non-porous materials include metals, glass, dense ceramic, and many plastics. Their materials are valued for their strength, durability, and resistance to moisture or chemical penetration. Because of their barrier properties, non-porous materials are essential in applications such as waterproof coating, food packaging, medical implants, and industrial piping, where protection, hygiene, and structural integrity are critical. Porosity and silica in epoxy formulations. When it comes to silica, its porosity plays a crucial role in modifying epoxy adhesives and coatings. Highly porous forms of silica, such as fumed silica and precipitated silica, contribute to thixotropy, reinforcement, and improved adhesion properties in epoxy formulations. Understanding how porosity influences silica's behavior in resins will help us make better material choices for enhancing viscosity, mechanical performance, and stability. So, what is silica? Silica or silicon dioxide SiO2 is an incredibly versatile material that plays a crucial role in formulation of adhesives, coatings, and resins. Known for its high surface area, durability, and reinforcement capabilities, silica is widely used to enhance the mechanical performance, control viscosity, and improve the stability of these products. Its inclusion in various formulations not only improves their properties but also ensures ease of applications, make it an essential additive in many industries. Silica exists in two primary forms, crystalline and amorphous, each with distinct characteristics that make them suitable for different applications. Understanding these differences between these two forms is crucial in selecting the right type of silica for a specific product or applications. Amorphous silica in particular serves as a key additive in adhesives and resins. It is commonly used as a thickening agent or filler in adhesives, coatings, and resin-based systems. Its ability to increase viscosity, improve flow control, and enhance rheological properties ensures that formulations are easier to apply and manipulate. This prevents issues like sagging or dripping during application, making it ideal for use in a variety of products. Fumed silica, a specific type of amorphous silica, is especially effective in epoxy, polyurethane, and silicone based adhesives. With its high surface area and fine particle size, fumed silica reinforces adhesive structures, improving both strength and durability. In resin applications, silica functions as a reinforcing agent in composite materials where it significantly enhances properties like strength, stiffness, impact, heat resistance, as well as chemical and thermal stability. This makes silica reinforced resins highly suitable for demanding industries such as automotive, aerospace, and constructions where performance under extreme conditions is essential. On the other hand, crystalline silica, which has a highly ordered atomic structure, is naturally found in minerals like quartz, cristobalite, and tridymite. It is valued for its hardness, high melting point, and chemical resistance, making it indispensable in applications like glass production, ceramic, and construction materials. However, despite its useful properties, crystalline silica dust poses serious health risks when inhaled. Prolonged exposure can lead to conditions such as silicosis and even lung cancer, making it crucial to adhere to strict safety protocols in workplaces where crystalline silica is present. When comparing fumed silica and precipitated silica, it becomes clear that while both are formed of amorphous silica, they differ significantly in their production methods, physical properties, and applications. Fumed silica is produced through the flame hydrolysis of silicon tetrachloride in a high temperature hydrogen oxygen flame. This process results in ultrafine high purity particles with a large surface area, low bulk density, and superior thixotropic behavior. Fumed silica is widely used as a thickening, anti-settling, and reinforcing agent in adhesives, coatings, and composites. Precipitated silica, on the other hand, is produced by reacting sodium silicate with acid, leading to the formation of larger, more porous particles. These particles have a higher bulk density and moderate surface area, making precipitated silica more cost-effective for bulk applications. It is commonly used in rubber, plastics, and sealants for reinforcement, as well as in the food and pharmaceutical industries as an anti-caking and flow aid. While both types of silica improve the mechanical properties of products, fumed silica is often preferred for its thixotropic control and dispersion qualities, whereas precipitated silica is more economical for bulk applications requiring fillers. Silica plays a vital role in epoxy formulations, improving adhesion reinforcement and stability. However, choosing the appropriate type of silica and handling it safely, especially crystalline silica, is crucial to achieving the desired performance. In the upcoming section of this series, we will delve deeper into the production processes and functional advantages of both fumed and precipitated silica, shedding light on their specific roles in epoxy adhesives and resin formulations, and more. Stay tuned for more insights.